So hello again for the second session of Machine Learning 101. In the last week, it was more of an introductory. We talked about application of machine learning, the metrics, error metrics, classification and regression problems. We had an idea, and we implemented our first algorithm, called K-neighbors algorithm. In this week, and we're gonna talk more about what's the neighbors algorithm, because it's famous and it's common. You would see it in a lot of machine learning activities. Okay, so if you go again, the approach, if you go again to Wikipedia and ask what's K-neighbors algorithm, in statistics, you mentioned the is mainly statistics and math. In statistics, the K-nearest neighbors algorithm, abbreviated KNN, the non-parametric method first developed by Evelyn Fix and Joseph Hodges in the 1951. So like you see, arkadaşlar, like machine learning, even though we hear about it now, but it was developed in the 1950s and even before, I guess. And later expanded by Thomas Cover. It is used for classification and regression problems for both cases. In both cases, the input consists of k-closest training example in the set. The output depends on whether the KNN used for classification or regression. Okay, I just want to highlight this non-parametric. What do you mean by non-parametric algorithm? Technically, for non-parametric algorithm, the one KNNs, more or less, that there is no training at all. At the training phase, just the algorithm store the training data, and everything happen in the runtime. That's what non-parametric. So like you don't have like linear regression, for instance, where you calculate weights and biases. You just store the training data and that's it. That's what do I mean by non-parametric, and it's important to know. So the logic of K-neighbors algorithm is easy. Tell me who your friends are, I will tell you who you are. Technically, that's what K-neighbors algorithm is. So like, for instance, if your friends are, let's say, love rock music, most probably you will love rock music also. And that's the logic of it. So they see the similarities between you and the people closest to you. So like you are as your family. That's the logic of it. For example, like the example that we had last week, which is like the setose and the flower example. So like we had like the sepal length and the sepal width and the target, which is the class 0 or class 1. And we had this beautiful plot. So what the K-neighbors algorithm will do when deciding, when in the runtime, while testing, what happens is like this. It's simplified by this one. Let's say that the red point right here is the new point that you want to predict if it is class 1 or class 0. So you plot it, and you see the closest points to it. And it is as the closest point to it. We see that the majority of the points near the point is of a class 1. So this point also should be of class 1. Like literally, this is the logic of K-neighbors algorithm. Classification arkadaşlar. Again, happen for class 0. It's the same thing. But we should, there's two questions here that we should ask. Like based on how many neighbors we are deciding. What do I mean by this? Well, here, as you see, as I mentioned last week, is a really literally perfect case. We have like class 0 and class 1 perfectly separated. So it won't really matter the number of cases that we're gonna choose, the number of neighbors that we're gonna choose, 1, 2, 3, 5, 10, maybe 100. But like in the case like this, look at it like the square, the blue squares is class 1, the red triangles of class 2. So what's gonna happen mainly is, here we have the point to arkadaşlar. So let's say we're taking k, which is a parameter that I'm gonna talk about it more later, equal 1. So like what does it mean k equal 1. So we will see the nearest point to this point, and they will have the same class. So it's going to end up by class k equal 1. Let's say that we decide to choose k equal 3. The nearest point to this point, and we see like the majority of the points are of a class A, class 1, or class 2, and then decide based on that. So in this case, if we take k equal 3, we're going to end up by predicting this point is of a class 2. Tamam mı arkadaşlar? Şimdiye kadar okay, wait in chat. Nothing. So I assume it's clear. Okay. Like after understanding the logic of, okay, I remember I want to talk when it's for regression. Let me open OneNote. Okay. Okay. Now the example that we talked about is classification example when we're trying to classify class 1 or class 2. But what if it is regression problem when we try to predict a continuous variable, like the price, for instance, last week? The idea is more or less the same, but the result is different. What do I mean by this? Let me like draw something right in here. Okay, this is not a perfect line. Okay. Okay, here's, and we're gonna plot the sizes that we have in our data set that we talked about last week. Like these are the data points. Let's say this of size, I don't know, 100, this 150, 200, 250, for instance. Now we're trying to predict the price of a new house. Let me change the color. Okay, so we have a house, let's say here. The size of the new house that we're trying to predict its price lays here. So what's going to happen if we choose k equal 1? We're going to see it, the nearest to it, and they will have the same price. When we take k equal 2, so we're going to consider this point and this point. So the price of the new house is going to be the average of the prices of the two nearest houses, and 3, etc., etc. So like that's how regression works. Well, I hope it's clear. Let me go back to the. Do you have a question before I go back to the presentation? I'm gonna assume you have no questions. Let me check the chat. Okay. No. So. Okay. Yeah. Let's say we understood like how k neighbors more or less work, but now we're gonna pass how to good parameters for our k neighbors algorithm and what we should take in account while trying to implement k neighbors algorithm. There's the scale of the data, which is like we're gonna talk about it, and the value of k, like as you see right here, the value of k decide our decision-making strategy. So what do I mean by the scale of the data? When we scale data, all the variables are equally taken into account, and that one variable is the decisive variable. What do I mean by this? So we said the nearest point. Tamam mı arkadaşlar? Like en yakın data hangisi? Okay, like technically nearest. As we mentioned, we all the time we need kind of how can I say this? quantity, like number, to quantify this distance. And usually we use the Euclidean distance, which like the square root of x squared plus y squared. But when the data is not scaled, let's say, for instance, like this one, our sepal length taken in meter, our sepal will be in centimeter. So our data will look more or less like this, 0.0051, and the other one is 3.5. So when we're going to calculate the distance, let's say we're going to calculate the distance from the origin, we're going to end up this thing, we're going to give us roughly 3.5. So what do we notice? That the sepal length feature, like almost we didn't take it into account at all, because the distance is mainly decided by the sepal width value. Tamam mı arkadaşlar? Scale the data, we will have more or less the same range. See how we fix the scaling of data. In practice, there's two methods. Well, not two methods, but today we're going to see two methods. Standard scalar, which is like method in scikit-learn that help us standardize the data. So we can bring everything into the same range of values. Not we have two big values and two small values. Second one is min-max. So here, like, okay, we're done with the scaling data thing. To choose as we said, why we should be careful while choosing the value, but the question how to do so. Well, in practice, you will notice that we can take the square root of n, and n is the well, you choose k as the square root of n. Like you can take the round of that, because it's not sure you're going to end up with an integer when you take the square root of n, the number of feature of data set. But when we use this method, we use this method of the square root is when it's expensive. Another thing, we're going to talk about it later. What do I mean by this? Okay, now we have 4 features, but this is kind of, you won't notice that a lot in practice, because more or less the features may take 100,000, even hundreds of thousands of features. So it may get computationally expensive if you want to try different values of k, because every time you need to fit a new model and everything. So you tend to take the square root of n, and more or less it will give you a decent result. Second one is the grid search is like a broad term, not just for k-neighbors algorithm. The idea of grid search is you try a lot of values of k and see which one leads to a better model. Like, for instance, see we're going to loop over 10 values of k from 1 to 11. And then we see which one lead to a better fit to our data, like which one lead to better accuracy and less error. Okay. When we talk about k-neighbors and k algorithms, may refer to grid search as the elbow method. Okay, so here the grid search, we took like 9 values, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 values of k, and we notice that, okay, you can see that we have, how can I say this? The better result with k equal 9, but we don't take the k equal 9, we take equal 3. Why is that? Because think about it like this, arkadaşlar. The more you will take k bigger on the training set, I'm just talking now on the training set, the more we're going to take k bigger, the more likely our model with on the training set. So it's more likely to overfit our data set. And overfit, we're going to talk about it next week, what's overfitting and underfitting. So think about it that our model will be focusing a lot on the training set. Also, our model will be faced with a new data points that it didn't see before. So it will be bad if our model kind of generalize its pattern to the training data set. There should be a margin between the training and prediction. Bu önemli arkadaşlar. Anlatabiliyor muyum? Anlatabiliyor muydum? Do you have any questions on this? Okay. So the idea of the elbow method is plot the k values as the x-axis and the y as the distortion or the error. And you see when the plot has effect, it's right here. So like there's this drastic change between, we have like the big margin, it's like, I guess, almost 1. Unlike here, which is like, well, it's getting lower and lower, but gradually. So we take this point that gives us this elbow. Okay, we're gonna pass to practice, but before this, what's the pros and cons of such an algorithm? Well, it's very simple, as you could see. It's intuitive. The logic behind it is easy, and there's few parameters. K, like literally we can just play with K. Well, if you go to scikit-learn, you will find other parameters, but the main parameter that it's the decisive one is the number of K values. Cons of such thing. Cons of such algorithm. It's not good enough with high dimensional data. What do I mean by this? So when we have a lot of features, our K-neighbors algorithm tend to do poorly compared to other algorithms. Doesn't work well with categorical features, sensitive to outliers. Well, I don't think we talked about categorical feature or outliers. That's why I think, let me open OneNote again. Talk about these two terminologies. Okay. OneNote. See. Okay, categorical feature arkadaşlar is something, it's kind of binary thing. It's like whether 0 or 1. What do I mean by this? Let's say we have a feature that tells us if a person is a male or a female. So let me, okay. Let's say we have a table and one of the columns is male. Other female. Okay, it's really terrible, but I guess you can understand. Okay, but like male and female, as they don't have a meaning because, again, we need some number, we need quantity to quantify this. What we tend to do is this is called a variable. If it's a male, our data point, our person is a male, we will have 1 right here, and of course 0 in female, and vice versa. That this is a categorical variable. Categorical variable is like indicate existence or absence of a certain feature. And K-neighbors algorithm doesn't do well on because the distance with such variables tend to be not, well, outlier. Okay, so we can, but it's important to understand this. Let's say we have kind of linear, okay. Think about this is like the side of the house, this is a progressive house. And we have kind of, okay. This is kind of a linear trend, right, arkadaşlar? What's an outlier? An outlier is a point like kind of this point right here. Why it's called outlier? Because it doesn't follow the general trend. Even though the size of the house is like small, it's really expensive. And this point is outlier. And usually what we do with outliers, arkadaşlar, there's two kind of things. Some people tend to delete them, literally delete outliers from the data set. Or some people, because also tell you something, which is like maybe another feature that you should consider for your decision-making thing. But we're going to stick to the simple thing, and I'm going to suggest you to, whenever you see outlier, delete it from the set, because it will affect your fitting, your training badly. Tamam mı? So our k-neighbors algorithm tend to do poorly if we have outliers in the data set, and if we have categorical variables, like a lot of categorical variables in the data set. Okay. So I'm going to pass to kind of practice now, and I go through everything. Let me need to close a lot of windows. Okay. So here, okay. So like I'm using Jupyter here on my local computer, not on Azure, not on Colab. I'm just doing it on my local computer using the Anaconda distribution. So let me open something. This is for reference. I created it before. So we're going to do our normal import s as PD. Let me just copy paste this. Okay, so like more or less you're going to find yourself importing this every time. Okay. And we're going to work with a real data set. Okay. This is PD equal, no, DF, it stands for data frame. PD. Classified data, yes. Classified data. Index call equals 0. Okay. So we're gonna work with. So like, let me explain this. For this data set, we won't know what WTT is or what PTI is. We just want to use these features that are known to predict the classes. And this kind of problem you may face it, especially when we talk about privacy, because some features you shouldn't know what they represent. I mean, in the real world, because it's kind of privacy thing. Okay. One way to look at it is like df.describe, I guess. df.describe is just a really beautiful tool that lets you thing like the count, the mean of that column, the STD, the standard deviation. You can use this to have an idea about our data set. And we have a mean of 0.5, which is like amazing because our data set is balanced low. So like we have 50% target class 1, 50% target class 2. Well, I couldn't notice it until now, honestly. So, well, this may take a while, but I'm gonna do it anyway. df hue equal target. Well, because we have 9, 10, let's say 10 features, and with the target class is 11. So it's gonna take a few moments. It doesn't mean that it crushes, but it takes time. This per plot give us, because it's figures, because it's plots, and honestly, they tell us general trend of what's happening with the features. Okay, well, it's too big, so you should. But what we see in general, features, we kind of have the separation between classes. Online class 2. Well, there is this kind of something in the middle, which is you're gonna find it in real life, arkadaşlar. But we can, a lot of features are dividing our target classes into more or less two separable features. This is kind of good to know. Okay, and it's okay. Let's say we're done with it. Now, let me go back right here. Okay. So if you look at the mean, it's like 0.94, 1.1, and we look at the max and min. Well, if you look at this data set, the difference of scale is not big. So like not for instance, features of 0.1 and features of 100. No, we don't. But we talk about between 0 and 2. And this is kind of good. But you should know that it is always a good practice to scale your data, even though the range is more or less acceptable, because scaling the data help you more, in general, boost the accuracy, boost the performance of your k-neighbors algorithm. Tamam arkadaşlar. And how do we do this? Okay. I guess from scikit-learn dot pre-processing import standard scalar. Okay, that's correct. No, it's not. Standard. Okay. Oh, okay, sorry. What's this? Okay. How do we work with the scalars? It's more or less like the same way we work with a model. So like we initiate the scalar. And then we fit scalar equal, no, df scaled, like the data frame scaled, equal scalar dot fit dot df dot axis. Now, if you look at it, and df scaled. Okay, so now we. No, I made a mistake. We just don't. So now we scaled. So like we have our more or less scalar model, and we trained it. Tamam mı arkadaşlar? So now transform. How do we have the scaled feature? Scale. Scaled equal scalar dot transform. Let me copy paste this. Okay. Feature. Let's bring them to the normal form. df dot airlock -1. Yeah. So now we have our scaled kind of data. Now you see like the value changed. Here we have like minus a lot of numbers, and from here they are, here they are different. So now our features more or less have the same scale. Okay. Now we're gonna choose a good K features. I will copy paste it from here. The train test split thing, and there's a lot of writing. Again, the same thing we did last week. Import the classifier, and then we're gonna go with K and neighbors equal 1 and see how it is done, and then we're gonna compare it to after we choose a good value of K. No, not this one. Predictions. I'm gonna write this. Dot report. If you have any question about the writing or the coding, you just can stop me. I can redo it. Yes. Yes. Here we more or less we're doing quite decently. Like we have F1 score of 93%. Class 0, 9% for class 1. But okay, we can squeeze a little bit more of what we can squeeze a better score. So we're gonna go with this one. Okay, it's a while loop here. Let me go through this. So here what I did was I just went through K from 1 to 40, the number of neighbors, and every time I did a new model with the new numbers, a new K number, and then I took the error rate. So this is what for loop is for. So, okay, I'm going to plot it later. Let me copy paste this. Okay. I use matplotlib here. Well, I'm going to share this with you, but that's not the point. Because so like we have a plot like this. Like this is the error rate, this is the K value. And if you notice that the more our K is getting bigger, the better results we're having. So elbow effect, like I said, because the number of data points that can play in, and like the way we took the error itself, because literally we will have the elbow method if we take the error based on the training. That's have the elbow effect. But if we take it used on the test dataset, we won't have that elbow effect. تمام arkadaşlar? I hope it's clear. But around like 26, maybe 27, we have kind of decent error rate. It's like the lowest, and still the same from 30 and beyond. It's the same. So we're gonna build a model. Okay, and then let's say better canon. Optimized, let's say canon optimized. opt equals and then opt. We built the KNN, the class, using 26 neighbors, which is like something like here. Well, I want to change it. I want to keep it 28. Let's see what happened. Let's take this 26. Okay. Here is just like fit it on the train and the prediction, and I'm going to do technically the same thing. I didn't import the confusion matrix in the first place. Where is the metric? Okay. I imported it. So look like we have better score. Well, not so better, but we can boost it from 1% for class 0 and for class 1, just by changing the k value to an optimized k value. And this is quite cool because it's difficult to boost a good score, but we managed to do so. Here, before ending this, I want to say that a mistake happened, and I made it on purpose, which is what? Let me go back. You don't want to do this. Okay, here. You see arkadaşlar, like I fitted my scalar on the entire data set. And if you remember, we talked last week that our model will be just all the phases of the development, just the training data set. But here by scaling, using the integrity of the data set, we're gonna kind of use the scalar that was fitted to scale the entire data set and including the training data set. So what's gonna happen is kind of, in a way, our model already saw, okay, like he has a taste of what the test set is going to be. And this is something that you don't do. So like the better thing is like you train and the scaling and everything should happen here. Okay, should have made them in one cell. But we should just fit our scalar on just the training points. No. And now x train equals scalar dot transform x. Now the scale, which is the result of this, let me print it, is the one we're going to use on train. Scalar that we trained on the training data set on the text in the test also transform it should happen like this, and then you should finish all your work like this. So the idea is your model, like whether it's scaling or anything, shouldn't see at all the test set. It should just see the training set. So it's a good practice to, after like having an ADE and see kind of more or less how the data look like. Split the data into training and test, so not confuse and have the same problem. Because what's happening in here? If we go and like scale our data set on and including our test set, and our model is seeing all the data set from the beginning, we will have, well, good results, but you don't know whether it is a good result or not because it's not real testing. You're like, imagine you're giving the answers to a student before giving the exam, and then you test the student on that exam. That is so biased. So yeah, like we came to finish this. Okay. Conclusion is now how to train and tune K-neighbors algorithm. And then later on, next week, we're going to talk about overfitting, underfitting, bias variance trade-off, and regularization. Do we have any questions? Yazabiliyorsunuz arkadaşlar. Okay, Beren is typing.
All clear, thank you.
Okay, thank you. You're welcome. Okay, so I'm finishing this right now, and share the repo again, find guided project and the solution of that project, so you can go and practice by yourself. I'm ending the meeting now. See ya.
Thank you, see you later.
Yeah.